Welcome back, everybody. This is our fifth session in JEE Mains previous year questions for chapter Magnetism and Matter of class 12th. Before this video, we have made four videos in this series, and all of those videos are available on our YouTube channel in the playlist section. We have also started similar series for NEET previous years. So if you are preparing, or some of your friends are preparing for the NEET, then they can also find those videos in the playlist section. If you find these videos useful, then do press the like button, share them, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, let's start today's video. In this video, we will be covering starting from I think 28 or 27. So this was the previous question which we covered in the previous class. Now start with the next one. Let me adjust pen thickness slightly. So the corrosivity of a small magnet where the ferromagnet get demagnetized is this: the current required to be passed in the solenoid of length 10 centimeter and the number of turns 100 so that magnet get demagnetized when inside the solenoid. So we have been given corrosivity, and we know that if we have a BH curve, if this is B, this is H, then on this H side we get the corrosivity, means value of H is given to us. So H is 3 into 10 raised to power 3. Now, current required to pass in the solenoid and the number of turns are 100 to demagnetize the magnet. So, to demagnetize the magnet, what we need to apply? We need to apply a negative field so that, or reverse field, opposite field, so that magnetic field reduced to zero. And in that scenario, we know that for a solenoid, B is equal to mu node Ni. And for a material, we know that B is equal to mu node H. Comparing both of these two, we get H is equal to Ni. So this is the required amount of current to produce this corrosivity and to reduce this corrosivity to zero. So value of H is 3 into 10 raised to power 3. N is number of tons per unit length, that is 100 tons in 10 centimeter length. So 10 into 10 raised to power minus 2. And I we will calculate. So this will be 10 raised to power minus 1. It will be 10 raised to power 3. So 3 into 10 raised to power 3 is equal to 3. 10 raised to power 3 into I get cancelled, or I is equal to 3 ampere. Option C will be the right answer. Let's move to the next one. An example of a perfect diamagnet is superconductor. This implies that when a superconductor is put into the magnetic field of intensity B, magnetic field inside the superconductor. Now we know that superconductors act as a perfect diamagnet, means it repels all the magnetic field lines trying to cross it. So if we have a superconductor, something like this, suppose this is our superconductor, then if there are some magnetic field lines trying to cross it, then they will be repelled along its surface, and inside magnetic field will be zero. So we can say option B will be the right answer here. Let's move to next one. Three identical bar ABC are made of different magnetic material which kept in uniform magnetic field. Field lines around them look like something this. So we have to find out diamagnetic, ferromagnetic and paramagnetic. We know that diamagnetic materials repel magnetic field, means And from here we can see that B is repelling magnetic field lines, so B will be diamagnetic. So B will be paired with D. And here we can see in the diagram A that all the magnetic field lines are passing through A. This is the type of behavior shown by the ferromagnetic material. So A will be paired with F and remaining C will be paired with the P. So AFBDCP option B will be the right answer here. Let's move to next one. Magnetic field of the earth at the equator is approximately this, and the radius of earth is mentioned. Then the dipole moment of the earth we have to find out. So movement of the earth is nearly order, and this field is given at the equator. So let me draw first. 3D representation might be helpful. Suppose this is our earth and our earth is rotated slightly. So this is our tilt, and now we assume that at the center we have a magnet. At the center we have a magnet, something like this. The color needs to be changed, better contrast. Suppose this is our supposed magnet of earth. Now we have been given magnetic field at the equator, so we have been given a magnetic field at this point. So this point act as an equatorial point for this magnet, and for a magnet like this, magnetic field value at an equatorial point is given by mu naught 4 pi m by distance cube, and that distance is the this distance, but here we will take radius of earth as the distance. So RE cube. So this will be, value is given to us 4 into 10 raised to power minus 5. This is 10 raised to power minus 7. M is as it is. And we have 6.4 into 10 raised to power 6 cube. Now solving this whole, we get M is equal to 1048 into 10 raised to power 20, and that is in the order of 10 raised to power 23. Option A will be the right answer. Now let's move to next question. The midpoints of two small magnetic dipoles of length d in end positions are separated by distance x, where x is greater than their we can say their dipole length. The force between them is proportional to x raised to power n, where n is, so we have to find the value of n. Now this is acting as a magnetic dipole, and this is also acting as a magnetic dipole. So let's take a point here A. Now at this point A, magnetic field due to this magnetic dipole will be B at A due to this magnet will be, as point A is on the axial line of this dipole, so magnetic field will be mu naught by 4 pi twice of the magnetic dipole moment divided by the distance, and as it is mentioned that distance is greater, so we take it as x, so x cube. Now force on some dipole due to other dipole is given by force is equal to dipole moment of that dipole times rate of change of magnetic field. So here we are taking in one dimensional field, so it is with respect to x only. So it will be m mu naught by 4 pi twice of m. 1 by x cube's derivative will be minus 3 x raised to power minus 4. So it will be minus 6 m square mu naught 4 pi x raised to power 4. So x raised to power is 4 or x raised to power minus 4 if we take it up, and it will be power will be 4. Now let's move to the next one. Two short bar magnets of length 1 centimeter each having magnetic dipole 1.2 and 1 ampere meter square respectively. They are placed on a horizontal table parallel to each other with their north poles pointing towards the south, and they have a common magnetic equator that are separated by a distance of 20 centimeter. The value of resultant horizontal magnetic induction at midpoint O on the line joining their center close to. So we have to find magnetic field at their center, and they both are oriented towards the same direction. So for that, let's first draw a diagram. Suppose this is our earth. I'm drawing it slightly big so that I can accommodate both of the magnets. This is earth, and we have this is our northern hemisphere, and this is our southern hemisphere, and we have south pole here of earth's field. Earth has a magnet, and we have a north pole here with earth as a magnet. Now we have two magnets. Suppose this is first magnet and this is second magnet. And let's draw the distances. They are separated by a distance of 20 centimeter. And they have a north pole here, south pole here, north pole here, south pole here. And it is not clearly mentioned here that it should be that this is the south pole of earth. There is difference between the south pole of earth and southern hemisphere of the earth. So we will solve for both of the cases that they are either pointing towards the south pole or they are pointing towards the southern hemisphere. If their north poles are pointing toward the southern hemisphere, then poles will get reversed. And we have to find the magnetic field at the midpoint lining join their center. So their centers, and we have to find magnetic field at this point. At this point O. Now at this point O, there will be three contributions. Suppose this is magnet A, this is magnet B, and we have an earth magnetic field also. So in this case, when north poles are pointing towards the south pole of the earth, not the southern hemisphere. So magnetic field due to magnet A, as this point O is on an equatorial line of magnet A. So magnetic field due to magnet A will be downward. And similarly for the magnet B, magnetic field will be downward. But for the earth, magnetic field will be from the north to the south. So from earth, magnetic field will be upward. So case 1, when magnet north pole point towards south pole of earth. So total field at point O, BO, will be, first of all, it will be northwards, and it will be magnetic field due to A plus magnetic field due to B minus magnetic field due to earth. Now earth's magnetic field is already given to us. We have to find magnetic field due to these two magnets. And as these are equatorial points, so magnetic field will be mu naught by 4 pi m1 by distance. Distance is 10 centimeter here. So 10 into 10 raised to power minus 2. So that will be 10 raised to power minus 1 cube plus mu naught by 4 pi m2, 10 raised to power minus 1 cube minus field of earth 3.6 into 10 raised to power, I think it is 5, or it should not be 5, it should be minus 5, because earth's field is very small. So this, from here we can take mu naught by 4 pi common, that will be 10 raised to power minus 7 divided by 10 raised to power minus 1 cube, so 10 raised to power minus 3 m1 plus m2. M1 plus m2 are 1.2 plus 1, that will be 2.2 minus 3.6 into 10 raised to power minus 5. So this will be 2.2 into 10 raised to power minus 4, and if we write this in terms of 10 raised to power minus 4, it will be 0.36 into 10 raised to power minus 4. So this will be something like 1.84 into 10 raised to power minus 4. And none of the options are matching here. So let's take the second case, that case 2, that magnets point towards southern hemisphere of earth. Now what will happen in this case? In this case, the poles will orient for magnet, poles will orient, and direction of their field will also orient. Now this is the north pole, as they are pointing toward the southern hemisphere for both of the magnets, north north, south south, and again point O is in their equatorial plane, means now their field will be something like this due to both of the magnets. So now all of these three fields will be added, and if they are added, the net field will be, in this case, field at point O will be just their sum. That will be 2.2 into 10 raised to power minus 4 plus 0.36 into 10 raised to power minus 4, that is 2.56 into 10 raised to power minus 4. And formula for here magnetic field will be BA plus B plus magnetic field due to earth. And if now we compare this answer 2.56, so we have it options, that is option B for us. So option B will be the right answer here. Now let's move to the next one. The Earth's magnetic field lines resemble that of a dipole at the center of the Earth. If magnetic moment of this dipole is close to this value of Earth's magnetic field near the equator or equator close to. So we have to find out value of magnetic field of Earth near the equator. And we know that equator point act as an equatorial point, means if we have a, this is, if this is our earth and our dipole inside the earth is something like this, dipole inside the earth is something like this, then equatorial plane of earth is something like this, means any point on equator act as a equatorial point for this dipole. And in these scenarios, magnetic field by dipole due at equatorial point is mu naught by 4 pi into m divided by the distance cube. Here it will be radius of earth. So it will be 10 raised to power minus 7 into m, that is 8 into 10 raised to power 22 divided by 6.4 into 10 raised to power 6 whole cube. So it will be 8 into 10 raised to power 15 into 10 raised to power minus 18 here. We will have plus 18 to minus 18 and divided by 6.4 cube. Solving this, we get 0.3 into 10 raised to power minus 4 Tesla. And we know that 1 Tesla is equal to 10 raised to power 4 Gauss. So it will be zero point 0.3 Gauss. That is option D for us. Now let's move to the next one. Relative permittivity and permeability of the material epsilon r and mu r respectively. Which of the following these quantities are allowed for diamagnetic material? Now for diamagnetic material, we know that mu r or permeability, relative permeability is less than 1, and for every material, for every material, relative permeability or epsilon r is always greater than 1. So we have to choose that option, and these two options are directly neglected as here epsilon r is 0.5. These two options are possible, and in that option B is possible as mu r is less than 1. Option D represents here paramagnetic material. This represents a type of paramagnetic material, and B represents a diamagnetic material. Now let's move to next one. Needle N1, N2, N3 are made of ferromagnetic and paramagnetic and diamagnetic substance respectively. A magnet when both close to them will. So N1 is ferro, N2 is para, and N3 is dia. So we know that paramagnetics are feebly attracted, diamagnetic are feebly repelled, and ferromagnetic are strongly attracted. So N1 will be strongly attracted, N2 will be feebly attracted, and N3 will be feebly repelled. So N3 repelled, N1, N2 strongly, so A is cancelled. N1 strongly attract N1 strongly, N2 weakly, and repel N3 weakly. So option B will be the right answer here. So with this, we end this video here. And again, if you find this video helpful, useful, then do press the like button, share it as much as possible, and subscribe to our channel. Also, if you want to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. With this, again, thanks for watching, and we will meet in next video.